Thank you for the introduction. And so this is the work mostly done by my student and also in collaboration with CF AMD. Okay. So this is the outline of my presentation, a motivation background and our method and result. Okay. So this is about analog IC placement. So this is transistor level. And the key point here is that we're trying to do performance-driven placement. Why we do performance-driven? Because if we look at analog circuit, this is one example of op-amp. The blue bars are the performance of schematic in the normalized scale. And after we do the layout, because of the parasitic, we see there's significant degradation of the performance, so that the layout has a big impact to the performance. Okay. Okay. So so then the question is, why not like we just minimize like a wire length, and in digital design, the placement, a common objective function is to minimize half parameter wire length. And so here we show that for analog circuit, it's a little bit tricky. So this is for one circuit. The horizontal axis is half parameter wire length, and the vertical axis are the gain and the bandwidth. You see the trend is not monotone, so it's not that you minimize the half parameter wire length, that's the best performance. That's not the case. Okay, so this is why we needed to directly optimize the performance instead of only do the wire length driven. Okay, so here are some challenges. One is about the models. Okay, so for analog circuit, if we use SPICE, that is too slow. So actually, we employed some machine learning model from some previous work. But the machine learning model itself, it is not differentiable. So in the optimization engine, we use Bayesian optimization. Okay, so then when we generate Bayesian optimizations in analog circuit, we also need to consider those constraints, for example, and the symmetry and those kind of constraints. We need to, so there's intertwined issue between those performance model complexity and analog constraints. So so we need to address this challenge, right? Okay, so we use like one previous work. This is a triple M. Triple M means like a machine learning based macro models. Okay, so the idea is that to build model at macro level, not the whole circuit. Okay, based on transfer function, and for the entire circuit, we can compose these macro model together to get the performance model. By doing so, we can get pretty good results, and at the same time, you know, we can reduce the data preparation time. But that work was mostly applied for sizing for analog circuit, was not layout aware. So we needed to consider this layout issue. So this is another issue we will need to address. Okay. So how to solve this issue, like this model and the complexity with those analog constraints? And one key approach we're using is to this variational autoencoder. Here I show you some background. So this is one input vector. For example, it can be an image. Okay, so a VAE, it is one generative machine learning model. So it has two key parts. One is the encoder, the other one is the decoder. So each can be one neural network. Okay, so given input vector, by encoding, it generates one representation in the latent space. The original VAE is a continuous space, and actually it is a probabilistic. And the decoder will sampling here to generate a new result, follow the same distribution at the input. This is the original idea of VAE. So that is can be applied similar as again to generate new data, right? Okay. And here we use another version of a VAE that is called like a VQVAE, vector quantized. The difference is that the latent space is discrete. So there is a code book. The code book is composed by a set of code words, similar as the case of channel coding. There are legal cases. So after the encoding, the result, they are continuous. First, we need to do quantization according to this code book. And then from this code quantized result, we generate the original space result. So this is VQVAE is the one technique that we use. So this is why we call our technique as this vPlace. Okay. So here, this is show you like this is how to train VQVAE. In our case, the input actually is a placement. We use a VQVAE to represent in the latent space, and the training has three parts. One is to make sure that after the decoder, it is still has a high pretty much consistent in the same space as the original one, and also that the training not only train the neural network but also generate the code book. Make sure the code book they're really good. And the reasons that we use the code book to capture those analog specific constraints, including non-overlapping constraints, we use those code book. And also this is the final one is that is the final solution, is close to the code book. So that is the one. Okay. So then the question is why do we use this VQVAE? Is that we use the VQVAE to capture, because these are trained from layout data, we can use them to capture those, roughly speaking, legalize the case. And there's another benefit is that the VAE actually can do dimension reduction in the latent space. And we use Bayesian optimization. Bayesian optimization has a scalability issue, so this dimension reduction is also helpful. Okay, here are a few previous work that we compared with. Align is an open source analog layout tool, but its placement is variance driven, and this is another work from Align project. This is a performance driven. It is based on simulated annealing. The machine learning model is a classification. So MM is triple M is a better model than this one. So these are the few previous work. Okay. So then this is the whole overview of this work. Okay. So the first part, we needed to generate data to train VAE model, and also we needed to train this layout aware performance model. Be careful, this is one interesting part. We train this model in the latent space, not in the original placement space. And then we do the optimization using Bayesian optimization. That is done also in this latent space. Okay, and here this is to show the improvements for this machine learning model. Okay, to capture the layout. Okay, so for the training data, there are a couple of issues about the training. So when we train the performance model, we needed to have some good layout. We also need to have some bad layout. Okay, because in Bayesian optimization, when it generates a new solution, it might be a bad layout. So the performance model needed to reflect the bad result. Okay, so this is why in the training data, we use Align to generate training data. We randomize the weight. So the blue ones is without randomization. With the red one with randomization, we can spread out to cover wider area. And this one shows us that by this training, we can get a better result. Okay, so this is show the framework of this. This triple M model in the latent space. It has a two-part. One is schematic information. The other one is this placement information. Be careful, this is in the latent space. Okay. Okay. As I mentioned again, the reason we use this Latin space is to enforce those constraints and also reduce the dimension. So this is an overview of this whole optimization flow. This part, the main loops of Bayesian optimization, this is in the latent space. It is a latent space. So one result, we will do the decoding, and then we do ILP-based legalization. And here we do need, so we use encoder to give a feedback to this machine learning model to provide feedback. Okay. So here I start to show some experiment results. This part shows the performance result in terms of gain, unit gain frequency, bandwidth, and the phase margin. These are normalized with our V-place. So we compared it to geometric driven, we can see there's a significant improvement. Our result is also better than the previous performance driven layout. Okay. So this one shows why VQ, VAE help. Okay, so by using VQ, VAE, we can improve the performance model accuracy, and also without using VQ, VAE, actually the results are not good. Okay. And this is to show the trade-off for different. The code book has many words. It has a different size. There's some sweet spot to pick up the good code book size. Okay. In the latent space, there's a vector length for the representation. The length also will affect the result. There's some trade-off here. Okay. Okay. So here's the conclusion that for analog placement, we need to consider performance beyond the geometric objective functions. We propose this V-place framework using the MMM model and do the optimization in the latent space. And it shows a pretty encouraging result. I think that's all. Thank you. Yeah.
Okay, I have a question. So for the Bayesian, usually for analog circuit, you have multi-objective. Mm-hmm. And in this Bayesian optimization method, you use weighted sum? Or
no, actually, so this one, the Bayesian optimization is focused on the performance, and overlapping and the symmetry constraint is considered actually by the code book in the latent space. Yeah.
So performance is in terms of, for example, dbGaN
or
like
yes, that's true. Yeah.
There
are multiple metrics. That
yeah,
part
yeah,
is, so yeah, you're right. That's true. Yeah.
Okay, so it's a weighted sum.
Yeah, that is weighted sum. That's true. Yeah, right. Yes. Yeah. Yeah. Yes.
Oh.
Very impressive work, Jiang. I'm just curious, when you built the architecture, when you say the quantizer, mm-hmm. It's basically just an integer. You quantize the output of the decoder with like an integral
this
formulation?
Is there's a code book. A code book actually it is many vectors. It is in the latent space. Many vectors. We after encoding, we pretty much needed to quantize aligned to those code book words. Yeah, right. Yes.
Because the locations are discrete.
Right. Yes. Yeah.
Thank you. Yeah. Thank you.
Yeah.
And right now, how many parameter is sent into Bayesian optimization for this work?
It's not big. These are just the placement. These are a relatively small circuit, just dozens of transistors.
Okay.
Yeah,
okay.
Right. Yeah. Right. Yeah.
Okay. If there